This is the last part of the invited lecture, and now being motivated by the new type of money and having built some background in cryptography, we are ready to delve into blockchain technology. Just as a bank account that allows a user to check, spend, or receive funds, Bitcoin Wallet is a software that implements similar functionality. Bitcoin Wallet contains one or more private keys. They could be stored in a file, or they could be stored in a wallet app. The private keys are used to spend funds, whereas Bitcoin address is a hash of the public key. So these two, public key and the private key, they're mathematically linked. And to obtain a Bitcoin account, a hash is applied to the public key. Bitcoin address is like a bank account that is used in receiving funds, Bitcoin. In terms of the length of Bitcoin address, it could actually vary, and typically about 26 to 35 characters long, while the private key is 64 character long, which is 64 times 4 is 256 bits is the length of private key. The first question that Bitcoin should address is verification. Verification of transactions. If Alice wants to send 2 Bitcoin to Bob, how do we know it is Alice who has approved this transaction and nobody else? Well, we've just discussed digital signatures, and digital signatures comes to rescue. The transactions on the blockchain are usually represented as simple messages with 3 fields, to, from, and the amount that has been transacted. Such messages are usually encrypted and passed along with the plain text unencrypted messages. So now the Bitcoin network could simply use the known public keys to decrypt the encrypted message and verify that plain text message and the decrypted message match. So that is the proof that indeed Alice has signed this transaction. I did forget to mention that private and public keys are generated at the time when wallet is created. Blockchain is the first technology to solve a long-standing problem of double spending. So double spending is a potential flaw in digital cash scheme in which the same single digital token can be spent more than once. So think of it as a file that you can copy in multiple locations. So when you copy a file, you don't have to delete the original file. So you can copy it as many times as you want. So this is not what we want, and that's what Bitcoin has resolved. This diagram demonstrates how the messages are sent by Alice to 2 different vendors as a payment for a service or a product. You can see that she does sign these 2 transactions with her private key, so both of the receivers could verify that indeed that's Alice who initiated these transactions, but they cannot check whether she has sent these funds to somebody else or not, and she is double spending. One solution to double spending problem is to introduce a concept of bulletin board that is called a mempool in Bitcoin terminology. And a mempool is a mechanism for storing information on unconfirmed transactions, and it acts as a sort of waiting room for transactions that have not yet been confirmed. So in this example, Alice constructs a message which states that she wants to send 2 Bitcoin to node N1, and she is node 3. This message is written to the mempool. Then Bob reads this message and checks whether there are some similar messages that Alice has sent earlier to somebody else. So in fact, he wants to verify that she has enough funds. So there are no other transactions. So Bob accepts this message, and it the message is stored in a database, in a ledger. But let's assume that Alice at about the same time has sent another message to somebody else, so also to Bitcoin, let's say to Carol. Then Carol reads this message and also checks whether there are some other similar transactions, in fact, whether Alice has the funds to pay her, and realizes that the total amount of Bitcoin that Alice has is 2, and she has just spent 2 Bitcoins to pay Bob. So Carol rejects this transaction, and this transaction is not stored in a ledger. In this scenario, Bob uses the funds that he has just received from Alice to pay Eve. This time there is no double spending because there are no other transactions from Bob in the mempool to some other recipients. So the centralized ledger or centralized mempool does solve the problem of double spending, but again, it requires trust. To decentralize, what if each node will have its own mempool in the ledger? That sounds like a great idea. However, the problem here is that how can we synchronize all of these copies of a single ledger? One solution is to broadcast every single transaction to everyone, so they're all included to the ledger by all nodes. Of course, after these transactions are verified. Having multiple copies of the ledger, there is no need to have or trust one single node or one single ledger or mempool that is centrally located. Unfortunately, this approach does not scale. Let's look at the following scenario to understand why. Say Alice advertises her payment to Bob, to everyone on the network. Bob received this notification first, since he is directly connected to Alice's node, and then checks that there is enough funds associated with Alice's account in his ledger, and say that there is. He then happily advertises to everyone the payment of these funds that he just received to Eve, for example. Carol gets this transaction and checks whether in her ledger Bob does have enough funds to pay Eve. And the verification unfortunately fails because, well, she has not yet received the payment transaction from Alice to Bob. While in Jessica's ledger, the transaction is accepted, since by the time she gets the message from Bob, she already received a transaction message from Alice. So you can see here Alice is directly connected to Jessica, and here the transaction will actually propagate a bit slow because it goes through Bob. So as a result, we have 2 different versions of the ledger on the network, and obviously here the order in which transactions are received do matter and might cause desynchronization in larger networks. Given that we have multiple versions of the ledger, which ledger we should use and distribute across the network? That is the question, and that is actually the central question in Bitcoin network. But before answering this question, a good idea would be to split the ledger, because it grows quite rapidly, into blocks. Perhaps we could assume that only last few blocks should be synchronized, and the rest of the blocks, the early blocks, are in sync. In this diagram, a full ledger is just represented as a list of blocks, but otherwise they are equivalent. Introducing this block structure, we have to address a few important questions. First of all, how can we be sure that the blocks are not rearranged in terms of their order? A clever solution would be simply adding a block number. The second question is, how can we be sure that the transactions in the blocks are not modified after we actually agreed to accept them? And here is another clever solution, is to add a digital signature or a hash of all transactions. So in that case, if some transactions are changed, then the hash computed on these new transactions will not match the hash that was computed before, and it will be easy to detect that something indeed has been changed. The third question is, how can we know that some of the blocks are not completely replaced, including the hash? Because if we check the hash and the transactions, hash of the transactions, then they will match if completely the whole block is replaced. Here is another interesting solution. So the solution is to link all blocks such that next blocks depend on previous blocks, and if something is changed in previous blocks, it will affect all consecutive blocks. So we can easily detect that. Finally, the main question still remains: which block should be appended to the ledger? So the idea here, we need to know how to reach the consensus that everyone agrees that this block should be the one chained to the blockchain. Visually, the answers to the first three questions in previous slide are depicted as shown in this diagram. So each block contains a block number, a hash or digest of all transactions, including the hash of a previous block. The hash of a hash is what actually links all consequent blocks. So every small changes in this block will affect the hash of all consequent blocks. Finally, we are back to the main question on how to reach the consensus on what block should be added to the blockchain. The idea here is to let each network participant or node to solve a puzzle that involves all transactions in the block. This puzzle should be computationally intensive, but the solution should be easily verifiable by all nodes. The node that solves the puzzle first adds its block to the blockchain, and all nodes should follow and agree to include this block to their ledger copies. Of course, given that the solution is correct, but again, they can easily verify that. The solution to the puzzle is a proof of work and guarantees that all copies of the ledger are in sync. Now, another advantage of such kind of system is that those nodes that successfully solve puzzles are randomly distributed across the network, and hence there is no single node that always decide what block should be chained to the blockchain. In the Bitcoin network, SHA-256 was used as a hash function, and the task is to find such input that results in a hash with d number of zeros. In the previous slides, we have seen that the hash is computed over the block number, all transactions in the block, and the hash of a previous block. Here we also concatenate a nonce. So that nonce is the only part that changes in the input to the hash function, and it's changed in a loop. So this is where the work is done. The difficulty of this puzzle depends on the parameter d that simply defines a required number of zeros in the hash value. So let's say d is 4, then the puzzle is solved on the 19th iteration in this example. So this hexadecimal digit 0 actually corresponds to 4 bits. That's why d is set to 4 here. Proof of work is great and it works, but why would someone spend his or her own electricity on solving such a silly puzzle? Well, no one would probably do that unless there is some kind of incentives. And in fact, Bitcoin network does incentivize nodes for solving the puzzle. Such nodes are called miners, and every node that finds a solution gets a Bitcoin reward. Currently, the reward is about 6.25 Bitcoin. This is, by the way, an interesting way to inject new money, new Bitcoin into the system. The reward halves every 210,000 1,000 blocks, which is approximately every 4 years. Overall, only 21 million of Bitcoin will be ever produced, and a block approximately mined every 10 minutes, and this interval is controlled by the puzzle difficulty, which is defined by the parameter d that we have just discussed. So the higher the d, the more zeros is in the hash, and the more iterations every miner has to go through to find a hash with this number of zeros in its hash value. We reached the end of the invited lecture. Some final remarks are that Bitcoin network is a decentralized system that does not require trust in peers. Transactions are validated by miners, and only one block at a time is included to the network, which solves the problem of reaching the consensus. But also it's important to keep in mind that I skipped some details due to limited time. However, the main concept of blockchain technology have been covered in this lecture, and you should have some ideas. One question that has not been answered is, what if there are two miners that solved their puzzles at the same time? Which of the blocks in that case should be added to the blockchain? I leave this question for self-study. I also encourage you to search online and study the famous Byzantine general's problem. And also feel free to ask me, Hannah, or any tutors any further questions. I find this technology fascinating and will be more than happy to discuss or answer any further questions. Thank you.